This video is about heats of formation. So the heat of formation, heat is sort of a slang word we use for delta H. The abbreviation for standard heat of formation or standard changing in enthalpy of formation. Standard is where that little degree comes from, and that means it's under standard thermodynamic conditions of 298 Kelvin. A standard pressure, we usually use 1 atmosphere. And the formation implies that we are forming something from its elements. And so these are values that you would have in a table somewhere. And that little subscript F is the formation, it indicates formation. And so you can see values listed for various substances. So I want to talk about first the definition. So here we're going to state the definition. The standard heat of formation is the standard delta H, or change in Gibbs free energy, associated with the formation of 1 mole of a substance from its elements in their standard states. So it's kind of important that you understand what all these words mean. Standard just means that we're under standard conditions. Delta H is the change in enthalpy, of course, from the as the reactants go to products. Standard delta H associated with the formation of, and so whatever you're forming, whatever the heat of formation is of, you're forming that. So that is the product. Formation, mole. 1 mole of a substance, and so that means that whatever you're forming, whatever the heat of formation value is given for, there's only 1 mole of that being formed, which means that the stoichiometric coefficient in front of your product is going to be a 1. The substances listed here would all be the products in their reactions from its elements, and so you're going to, these would be the whatever elements make up that substance would be the reactants in these reactions. They're standard states, and so you need to know the standard states of the various elements. Most of them you already know. All of the metals would be listed as monatomic metals in their solid state, except mercury as a liquid. Some elements exist in diatomic form, like hydrogen, nitrogen, oxygen, and all of the halogens. Most other substances I would either give you the standard state or I'll let you know if you need to know them. Graphite is the standard state of carbon. Sometimes it's just listed as carbon solid. We're going to do some practice problems associated with this. So here are 2 practice problems we're going to do. So here we're going to write a balanced chemical equations that correspond to the delta H of formation of what appears to be iron 3 bromite solid and silver nitrate aqueous. So keep in mind that a delta H of formation means that we're forming those substances, which means that they are definitely products. They are the only product in the equation. So you're going to write FeBrO23 as the product, and then an arrow. And then you need to separate this compound into its respective elements. There are 3 elements present: iron, bromine, and oxygen. So we separate those. Then you need to write each of these in their standard states. Standard state of iron, because it is a metal that is not mercury, is just Fe by itself, and it is a solid. Bromine's diatomic, and it is a liquid. Oxygen is diatomic, and it is a gas. The last thing you have to do is, because these are heats of formation and they are in kilojoules per 1 mole of the substance that you are forming, that means that the product that you write, there has to be a 1 coefficient in front of that. Now that makes things kind of complicated. It means on the left that we need to use fractions. So there's 1 iron on the right, which means there's 1 iron on the left. That one's easy. But there are 3 bromines on the right, and there are only 2 bromines on the left. But we can't use a whole number stoichiometric coefficient for Br2 in order to get a 3, right? So you need to make that 3 halves Br2. And then there are 6 oxygens, which means we need a 3 in front of the O2. And that's done. Now if we move on to silver nitrate, we're going to write silver nitrate aqueous as the product. And then the arrow, we're going to divide that up into its elements. There are 3: silver, nitrogen, and oxygen. Silver solid is the standard state of silver. N2 gas is the standard state of nitrogen. And O2 gas is the standard state of oxygen. We need a 1/2 in front of the nitrogen, and we need a 3/2 in front of the oxygen to make that balanced. Number 2, consider the following diagram with reactions and their corresponding delta H values. Now this is an interesting problem. It kind of combines a lot of information that you've learned so far. Some of it is related to Hess's law. Some of it is related to these enthalpy diagrams where the enthalpy is on a vertical scale. And it also relates to heats of formation, which is why it's in this part of the practice set. So we see in our diagram that we have 6 on the very bottom. The lowest enthalpy here is 6 moles of graphite plus 3 moles of molecular hydrogen at the very bottom. And then benzene, C6H6 liquid, is in the middle. And then at the very top, C2H2, that is a compound called acetylene. And you can see the arrows there. So the arrows are reaction arrows. And so the arrow on the left, the negative 680.31 kilojoules, that is the delta H associated with 3 moles of acetylene decomposing into 6 moles of graphite and 3 moles of hydrogen. And then the other one that you see, the other arrow, would be benzene, C6H6, converting into 3 moles of acetylene. And you can tell that just based on the direction of the arrow. So part A, based on this figure, we're going to determine the change in enthalpy associated with 3 acetylenes going to 1 benzene. So what you see there is 1 benzene going to 3 acetylenes, and that has a delta H of positive 630 kilojoules. But what we want is the opposite reaction going in the opposite direction. So that's going to reverse that arrow, and it's going to reverse the sign. So it's going to be negative 630 kilojoules. Part B, we're going from liquid benzene into its elements. If we compare that to what we see, benzene is here, and we're going to the individual elements. Now what you notice is that there is no arrow currently on here that corresponds to this particular reaction. However, we do have a combination of 2 other arrows that have the same initial and final state. So we know these 2 arrows, and since they have the same initial and final state as this arrow, that means that we can just add them together. So 630 plus negative 680.31 gives me negative 50.31 kilojoules. And that makes sense based on the size of that, based on the sort of size of this arrow, and it's negative, it goes down, right? So you'll notice here that if we have the initial state, C6H6, and we have this arrow going down to the final state, that's what B is asking for. But we don't have that. We have the initial state here, and then we're going up and down again. But because they have the same initial and final states, we just need to add them up. This is delta H1, this is delta H2, and this is the overall value, this little arrow here. It appears to be accurate to the ones place because there's a period right there. So there should be a dot here, negative 50 dot kilojoules. It should have 2 sig figs. That 1 0 in the ones place is significant. Part C, we're going to do the heat of formation of liquid benzene. So what you'll notice on here is that the heat of formation of liquid benzene, benzene is here, and we're going to form it from its elements in their standard states, and those are down here. So it's this blue arrow that we're looking for. And we just calculated the orange arrow, which is just the opposite direction. So that's going to be positive 50 kilojoules. That one I did put the dot on there. Last but not least, part D, heat of formation of gaseous acetylene in kilojoules per mole. Now, I think, so the acetylene up here is in the liquid phase, and I think this is a mistake on my part. You can't actually answer the question for gaseous acetylene. I should have changed that to liquid acetylene. I didn't notice that mistake. So this should read delta H formation of liquid acetylene, C2H2, in kilojoules per mole. The reason is because liquid acetylene is on this diagram, and you don't have enough information to know the difference between the gaseous and the liquid forms. So that's just a typo here. Okay, so heat of formation of liquid acetylene in kilojoules per mole, if we think about that, we're forming C2H2 from the elements, which are down here in their standard states, but it's in kilojoules per 1 mole, and what we have here is 3 moles. So here we have the decomposition of 3 moles of acetylene, and we want the formation of 1 mole of acetylene. So that has two differences with what the reaction that's shown here. It's related to this negative 680.31, but we need to invert the sign and make it positive, and we need to divide it by 3 for 1 mole instead of 3 moles. So we're going to here from here, which means we need this arrow in this direction. So we're going to make it positive 680.31, and it's for 1 mole and not 3. So it's 680.31 divided by 3, which is 226.77, which is really 680.31. That is accurate to the hundredths place. Divided by 3 isn't going to change that. Yes, that's actually more accurate than the other numbers, so that's actually correct. It's got all 5 sig figs. So this practice problem is using heats of formation, or the change in enthalpy delta H under standard conditions, that's associated with the formation of these compounds from their elements in their standard states. So we're going to use, this is just an example of how we use heats of formation. So we're given an equation. This is combustion of glucose, and we have heats of formation values in the table at the bottom. So whenever you're trying to calculate these, remember that delta H is that anytime you have a delta, think about it as final minus initial. So in a chemical reaction, the final state is the product state, and the initial state is the reactant state. So that might help you remember that when you're calculating the delta H for a reaction given heats of formation, the equation you're going to use is the delta H reaction equals the sum, that's what this capital sigma is, the sum of all the heats of formation of the products, and then you're going to subtract from that the sum of all the heats of formation of the reactants. Now, the stoichiometric coefficients are also important because remember these heats of formation are given in kilojoules per mole, so that's 1 mole. So in this reaction, you are using 1 mole of glucose, but you're using 6 moles of oxygen and 6 moles of carbon dioxide, and you're forming 6 moles of water. So those 6's, you're going to multiply this kilojoules per mole times 6 moles of CO2, or whatever the stoichiometric coefficient is. So here, we're going to look up the products first. I'm going to list this out first. So we have 6 times the heat of formation of carbon dioxide, plus 6 times the heat of formation of water, minus the heat of formation of glucose, solid, plus 6 times the heat of formation of oxygen, gas. So here I'm just plugging in the reactants and the products, their identities, plus the stoichiometric coefficient. And now we're going to go down here to this table, and we're going to look these values up in the table. So CO2 in its gaseous form is in the table right here. So we're going to put that number in, negative 393.5. Water, H2O, is here, 285.8, minus, and then a big parentheses, we're going to, glucose is here, negative 1273.3. Now we're at oxygen. Okay, so O2 gas is not in the table, right? We can't find it in the table. It's not here. And the reason it's not here is because this is a special condition that we need to talk about. And this is here. So elements like oxygen, when they're in their elemental form, like O2, in their standard states, and so the standard state would be the most stable state under thermodynamic conditions, under thermodynamic standard conditions. And so oxygen is diatomic in its most stable state, O2, and it's a gas at standard temperature and pressure. And so all elements in their standard states have a delta H of formation of 0. So let's talk about elements in their standard states. They have to be elemental, elements in their standard states. Delta H of formation of 0. That's important. When you can't find it in the table, check and see if it's in their standard state. So here, standard states, H2, O2, so hydrogen, oxygen, nitrogen, those are all diatomic and they're all gaseous. All of the halogens are diatomic, F2, Cl2, Br2, and I2. Now they're not all gases. Fluorine and chlorine are both gases at room temperature, but bromine is a liquid and iodine is a solid. Metals just tend to be solid, except for mercury, of course. Most other elements, a lot of the noble gases, of course, are gases, and they're monatomic, helium, neon, argon. There are a few others that we might talk about. For example, carbon's standard state is graphite. But we will talk about some of those. And so you're going to plug in a 0 here is the main point, the main gist of that. So now when you add all this up, you get 2361 minus 1714.8 minus a negative 1273, which means you're adding 1273. So at the end of the day, what you get is negative 2,802.5 kilojoules. It looks like it's accurate to the 10th place because you're just adding some numbers up and all of these other numbers are accurate to the 10th place. Okay, one more example. Using the thermodynamic data provided, determine the change in enthalpy for the following reaction. So the thermodynamic data provided are going to be heats of formation in a table, delta H of formation values. So remember that when you're using heats of formation, the equation you use is here, the sum of the heats of formation of the products minus the sum of the heats of formation of reactants. I'm going to fill those in using the equation that I'm given. So 2 times the heat of formation of liquid water plus 2 times the heat of formation of bromine liquid plus 4 times minus, all that in parentheses, minus 4 times the heat of formation of HBr gas plus oxygen's heat of formation. We're going to go to the table. Those are shown here, 3 different tables. We're going to come back and see what we're looking for. Water is here, negative 285.83. We'll plug that in. And then bromine is in its standard state there. And then HBr, we'll look up on the table, and that is here, negative 36.3. Plug that in, and then O2 gas is 0. So we plug those numbers in, and you get negative 571.66 plus 145.2. And that's going to give you negative 426.46 kilojoules. It's accurate to the 10th place because the least accurate number in the table is accurate to the 10th place.